Alright, so we've gone over igneous rock, we've gone over sedimentary rock, and last but not least, we'll talk about metamorphic rocks. But first, let's discuss a bit about what metamorphism is. And most generally, metamorphism is a rock's response to new conditions that don't involve melting. But what are these conditions specifically? These conditions are a change in temperature, a minimum of a 200 degrees Celsius increase in its temperature, an increase in the confining pressure. So basically, burial under the ground by quite a bit of rock on top, but sort of an equal kind of pressure on all sides of the rock. This could be differential stress, so an uneven sort of shear type stress on the rock. And the last is underground, you get these hydrothermal fluids, which can transport elements and ions around in a process called metasomatism. And this can change your rock in a number of ways. Firstly, the pressure especially can lead to the reshaping of crystals, often flattening them and elongating them. This is a thin section under a microscope of a metamorphic rock, and you can see that the individual mineral grains are really flattened, they're longer, and you can immediately tell from that that this is a metamorphic rock. Another way rocks can change is the formation of new minerals, new crystals within the rock, using all the atoms and elements that were in the rock before. So the crystals sort of reform themselves to better hold themselves together thermodynamically with the new temperature and pressure conditions. And the last, again, going back to metasomatism, is the transportation of new materials, new atoms, new elements into or out of the rock using these hydrothermal fluids. And the exact response of a rock to its new conditions depend on the rock's initial composition, the exact pressure conditions, is it buried a little bit or a lot, and again the exact temperature conditions, is it somewhat warm or very warm. But again, it can't be too warm or else the rock may melt and it won't be a metamorphic rock, it'll be an igneous one. And just for clarity, your initial rock could be before metamorphism, or your protolith could be a sedimentary rock, it could be an igneous rock, it could even be another metamorphic rock being even further metamorphosed. So we've talked about temperature and pressure a lot, which are the two sort of base metamorphic conditions. But again, there are as many sort of sets of metamorphic conditions as there are unique combinations of temperature and pressure. But for simplicity's sake, we do group these into four different categories. First, there is burial metamorphism, which is a very low-grade metamorphism, low temperature, low pressure, sort of here on our chart. There is thermal metamorphism, which involves really high temperatures but fairly low pressures, and this usually occurs in the presence of an igneous intrusion. The hot magma increases the temperature on the surrounding rock, but does not really change the pressure very much. And that would be sort of here on our chart where you see the hornfels. Next, there is subduction zone metamorphism, where you get a big chunk of oceanic crust sort of subducting going under continental crust. And this puts a lot of pressure on the subducting crust, both due to the fact that it's being buried under the continental crust and also because of the pressure from the collision. However, it doesn't really increase the temperature very much, at least not initially. So what you get is lower temperatures but still very high pressures, and this would be sort of this blue schist eclogite axis on our graph here. And the last is regional metamorphism, sort of in the middle, where you see the temperature and the pressure increasing together sort of proportionally. And this would be this axis going from sort of green schist to amphibolite and going all the way over to granulite. And in regional metamorphism, we classify rocks based on their metamorphic grade. So high-grade metamorphism occurs when you have high temperatures and high pressures proportionally. And sort of medium grade would be medium temperature, medium pressure. And then when we're talking about low-grade metamorphism, we're more referring to that burial metamorphism, those initial stages of metamorphism. So we'll start with regional metamorphism as an example, and we'll use the example of the shale-derived rocks. As you know, shale is a sedimentary rock, and we're talking about the metamorphic rocks that are formed from the protolith shale in increasing temperature and pressure conditions. So we'll sort these by metamorphic grade. We'll start off with the slate. Slate's low metamorphic grade, low temperature, low pressure. And you can see that these sort of slabs of slate form. We get these linear features, which are known as foliation. But it hasn't changed too much as of yet, except for maybe the appearance of being cooked a little bit. We then move to a rock called, phyllite, which is not pictured here, and then a rock called schist, where we see a lot more changes to the crystal structure happening. And then from schist, we move to the very high-grade gneiss, where we actually get to start to see the mafic and the felsic minerals separating themselves into these light and dark bands. So the light bands are felsic, and the dark bands are more mafic minerals. So now onto contact metamorphism. These are those hornfells on that diagram from earlier. Again, high temperature, low pressure, often found near an igneous intrusion. And you'll often see these hornfells in this sort of halo type formation, this which is called an aureole, around the intrusion. So once the intrusion cools down and solidifies, and once all this rock up above gets eroded, what you'll end up seeing is this halo of metamorphic rock, specifically hornfels, surrounding these intrusive igneous rocks here, perhaps a granite, for example. Now on to subduction zone. Again, you see the subducting slab. It is under quite a bit of pressure from all the stuff above it, as well as the collision. However, you see these temperature lines. These are called isotherms, indicating that it is quite a bit cooler in the slab itself than in the surrounding rock. And in addition to that, you get the effect of water that the slab drags down with it from the ocean. And what you get is this class of rocks called eclogites, as well as blue schists, which form in a combination of these conditions, and due to the fact that they are sort of mafic in composition, coming from basalt or gabbros. Now, in addition to all the types of metamorphism we went over earlier, there's also local metamorphism. Local metamorphism is caused by very high energy events that occur over a short period of time. And there are two good examples of this. The first is a meteorite impact or an asteroid impact. And these produce formations called shatter cones, like the one you see here. This is actually from the Charlevoix region in Quebec, former impact site. And another one is actually when lightning strikes sand, introducing a lot of energy, a lot of high temperatures, producing these rocks called fulgurites, which are again created when lightning strikes sand. Now again, we did mention at the beginning that metamorphism is a rock's response to a change in its conditions, a change in its surroundings. And a change doesn't just mean an increase in temperature and pressure, it could be a decrease as well. And a great example of this is when you take rocks that hail from the mantle and you bring them all the way up to the surface. And this is exactly what's happening with those peridotites I mentioned earlier from Gros Morne in Newfoundland. This is actually my picture of some peridotite from Gros Morne, and you see this sort of scaly black rock forming on it. That's actually serpentinite, which is a retrograde metamorphic rock which forms as the peridotite responds to its sort of new lower temperature and pressure conditions at the surface. So that's it for metamorphic rocks, and actually that is all for rocks. And in the next segment, in the next series of recordings, we'll start getting into structural geology. Thanks for watching.